this $2 billion telescope prove we're not alone? Right now, across some of the most remote places on Earth, humanity is building a machine so powerful it could hear faint alien radio leakage from tens of light years away. In this video, I'm going to show you how the Square Kilometre Array, spanning 2 continents, will peer back to the birth of the very first stars, hunt for dark matter, catch gravitational waves using the Milky Way as a detector, and yes, seriously search for extraterrestrial life. You'll also see the insane engineering challenges, the mind-blowing discoveries its Precursor telescopes have already made, the human story transforming science in Africa, and the surprising controversies that almost no one is talking about. So, what exactly is the Square Kilometre Array, also known as the SKA? In short, it's a radio telescope, but that description doesn't really do it justice. When it's fully operational, it will be the most sensitive radio telescope ever built, with a total collecting area of roughly 1 square kilometre, hence the name. The SKA is split across 2 sites. In the Karoo semi-desert of South Africa, 197 large dish antennas, each 15 metres across, are being arranged across a region stretching more than 150 kilometres, an area so large it effectively turns the landscape itself into a telescope. This is the SKA-Mid array, designed to pick up mid-range radio frequencies. Think of it like a giant ear tuned to a very specific part of the electromagnetic spectrum. Then, over in Western Australia, in a remote stretch of the Murchison region, there are over 130,000 smaller antennas. And yes, people often describe them as looking a bit like metal Christmas trees scattered across the red desert sand. This is SKA-Low, focused on low-frequency signals from the very early universe. Together, both sites are operated under a single organisation, the SKA Observatory, or SKA-O. It's an intergovernmental body backed by 16 member nations headquartered in the UK, with Germany becoming an official member as recently as 2024. Construction is ongoing, and scientists expect the full telescope to begin scientific observations around 2028. In fact, the very first SKA-Low images were already taken in March 2025, even before the full array is complete. The total cost, around €2 billion, which when you consider what it's designed to do might actually be a bargain. Here's where things get really exciting. The SKA has a list of scientific goals so ambitious it reads almost like science fiction. Let's walk through a few. In the first billion years after the Big Bang, the universe was mostly dark, a fog of hydrogen and helium. Then the very first stars switched on, and their light stripped electrons from that hydrogen, fundamentally changing the cosmos. The SKA is specifically designed to detect the faint radio signals left over from this era. With 1,000 hours dedicated to cosmic dawn, it could be the first to see the universe's first stars switch on. We've never directly observed this moment in cosmic history. This would be the first time we actually see the universe wake up. We know that the ordinary matter we can see, stars, planets, you, me, makes up only about 5% of the universe. The rest is dark matter and dark energy, and we barely understand either. By mapping hundreds of millions of galaxies and how they move, the SKA can help us trace the invisible scaffolding of the universe. The SKA will use pulsars, rapidly spinning neutron stars that pulse with extraordinary regularity, as a kind of cosmic clock network. By watching dozens of these pulsars simultaneously, it can detect ripples in space-time passing through our galaxy. It's like using the Milky Way itself as a gravitational wave detector. The SKA will be powerful enough to detect the kind of radio leakage from a planet like Earth at distances of tens of light years. If there are technological civilizations out there broadcasting into space, this telescope has a real shot at picking up the signal. Building a telescope of this scale comes with engineering challenges that have never been faced before. Consider the data problem alone. The SKA will generate staggering amounts of data, at peak, more raw data every day than the entire global internet once handled, before being reduced to around 600 petabytes a year for long-term storage. Processing that requires 14 global data centers, from Europe to China to South Africa, running AI algorithms to sift signals from noise 24/7. Germany, for example, has set up the German Center for Astrophysics in Görlitz specifically to help handle this. Their job is to reduce that massive data stream to manageable quantities without losing any valuable astronomical information. It's one of the most ambitious data science challenges ever undertaken. Then there's the hardware. The engineers at OHB Digital Connect, in cooperation with the Max Planck Institute for Radio Astronomy, supplied 14 antennas to the South African site, and was later commissioned to provide 86 additional high-sensitivity receivers. South African landscapes, German engineering, and global coordination, all working in concert. The remote locations are also critical. Both the Karoo and Murchison regions were chosen because they're among the most radio-quiet places on the planet, but now they're under threat. Mega constellations like Starlink and Amazon's Project Kuiper could flood these silent skies with radio interference, potentially swamping the SKA's ability to detect the faintest cosmic signals. SKA-Low is fighting back through UN channels for satellite operators to coordinate beam avoidance and reduce emissions. But behind all of this engineering, there is a human story that deserves to be told. When this project began, there were only a handful of professional astrophysicists in the whole of South Africa. Today, there are several hundred. The SKA-Low has poured investment into schools, universities, and research programs, not just to host a telescope, but to build an entirely new scientific generation around it. Victoria Samboko grew up in Mozambique. Access to telescopes, to research labs, to the international scientific community, these things were not part of her world. Today, she is completing her PhD at Rhodes University in South Africa, and the method she developed for reducing solar interference in radio astronomy observations is used by researchers worldwide. She says the SKA funding changed her life, not in a small way, in the way that determines what a life becomes, who you meet, where you travel, what you get to contribute to. She describes being part of a project of this scale as something she couldn't have imagined when she was starting out. That is what this telescope is doing on the ground right now, before it has even finished being built. South Africa isn't simply hosting the SKA, it is being transformed by it, and that transformation of a continent's scientific capacity, of individual lives, of what becomes possible for the next generation of researchers across Africa, may turn out to be one of the most lasting things this project ever produces. Some discoveries will be written in the stars, others will be written in the careers of people who finally got a seat at the table. Now, no big story is complete without some complications, and the SKA has them. In August 2025, whistleblower allegations emerged claiming the SKA-Low had lost £12 million through risky investments in money market funds, with one fund reportedly losing 45% of its value. The claims also included procurement irregularities and a toxic work environment, with staff allegedly facing bullying and unfair dismissals. On top of that, Australia's government contribution to the SKA-Low reportedly increased by more than $150 million Australian dollars from 2020 to 2024 compared to initial budgets. Spokespeople attributed part of this to foreign exchange fluctuations and adjustments, but the overspend is significant. The SKA-Low denied any wrongdoing, and an independent external evaluation of the allegations was commissioned in response. It's important to be clear, these are allegations, not proven facts, and mega-projects of this scale, with complex governance, 16 member states, and billions of euros at stake, are genuinely difficult to manage. But the SKA is an intergovernmental organisation, which means it isn't subject to national laws in the way a regular company would be. That raises real questions about accountability and transparency that the member governments will need to answer seriously. The outcome of that independent review will matter a lot, not just for the project's credibility, but for how we structure international science going forward. Here's some good news though. We don't have to wait until 2028 to see what this telescope network can do. Smaller, Precursor instruments, built on the same sites as a kind of proving ground, have already been delivering extraordinary science. Meerkat, the 64-dish Precursor in South Africa, produced a radio image of the Milky Way center revealing 10 times more elongated radio filaments than had ever previously been observed. Nobody fully understands what those filaments are. That's not a problem. That's exciting. In Australia, the MWA telescope discovered a completely new type of radio transient, an object emitting powerful blast every 18 minutes, far longer a period than anything previously known. No one knows what they are, how they are powered, or whether they are all even the same type of object. And ASKAP, another Australian precursor, identified a strange new class of objects called odd radio circles, giant rings of radiation visible only in radio waves, whose origins remain a mystery 5 years after their discovery. These aren't just technical test results. These are truly new phenomena, things we didn't know existed before we started building the SKA, and they represent a fraction of a percent of what the full array will be capable of. I'll be honest with you, the more I researched this project, the more it moved me. Not just because of the science, but because of what it represents. Hundreds of scientists who didn't exist in this field a decade ago, all pointed at the same horizon, asking the same ancient question. Are we alone? We have been asking that question for as long as we have been capable of asking questions at all, and for the first time in human history, we are building something genuinely capable of answering it. That to me is worth every euro, every engineering headache, and yes, even the governance problems that need fixing. The controversies are real, and they matter, but they are the problems of an institution still learning how to carry the weight of something this significant. I hope the people responsible for the oversight get serious about that, because this project is too important to be undermined from the inside. And here is the question I keep coming back to, the one I want to leave with you. If this machine does its job, if it actually picks up a signal from a civilization tens of light years away, what do we do next? We've spent billions learning how to listen. Have we spent any time at all thinking about what we say back? If you enjoy stories about the architecture of ambition, the engineering, design and construction behind world-changing projects, this channel is where I'll keep digging into them. I'd be truly grateful if you joined us for the next one. The answer may be out there, but the greater achievement is that we built something capable of asking the question this beautifully.